our next set of notes. Next set of notes is going to deal with another factor affecting the way our Hardy-Weinberg equilibrium works, and that is migration. Hardy-Weinberg assumes there are no migration whatsoever, but we know that doesn't occur. We're going to look at how the alleles are changed within a population based upon migration. So we're going to look at delta P, the change in the P value in a population per generation. The way we're going to do that is we're going to use this example here. If regular P is the frequency of big letter A, and then P sub M is the frequency of immigrants that are coming into a population. I can also do this for immigrants as well, but it works better for immigrants because I'm trying to see how it's affecting the population I'm looking at from other populations coming in. So I'm going to try to figure the delta P out by utilizing these two numbers. M is the coefficient of migration, and that's the proportion of migrant genes entering the population. So how often does that occur? What percentage is coming in? So it would be something like this. My delta P is my coefficient of migration times the quantity, the population, or the migrant population minus the current population's P values. So I can see the difference between these two multiplied by the coefficient of migration. Coefficient of migration has to be figured over multiple years. So in case of our class, you'd be given a problem with the M value already given to you. Otherwise, you have to do years and years of research to figure that value out based upon different factors of how things are passing back and forth between different groups. But it's a pretty straightforward equation like that. So as long as you've been given the values here, you know a couple of values here, you're able to figure this out. Plug it in and be able to solve the problem. So the example problem, my P value is 0.6. The value of my P coming in for the migrant population is 0.4. My coefficient is 0.1. So in order to figure this out, I'm going to take this minus this. So that's going to be negative 0.2 times 0.1. And this is an absolute value because I'm really losing part of the population, but the concept is my change is going to be 0.02 absolute value. So the effect on allelic frequencies depends on a couple of factors. One, the size of that M value. If I have a much larger M value, that means the coefficient of migration means it has a bigger impact. That's going to make a huge deal on how I'm changing this concept. Because multiplying times that number is going to make a difference. The big difference between these two values. If these two values, let's say this was only 0.2 in the population, but the migrant population is going to be 0.9, all of a sudden that's a huge difference. It's a massive number, and then the coefficient's high, you're going to have a big impact. But in general, they tend to be very similar, unless you have some weird population coming in that's changing everything altogether. You had a bunch of pigeons that all had a trait for blue feathers, and all of a sudden, from Europe, they bring in a bunch of ones that have brown feathers, and that really drastically, let's say they have a high percentage of them and a high number of them, and all of a sudden that really changes the overall population we have here. You start seeing more brown pigeon feathers. That would be an example of how that would work. Selectional advantage. One of the words we use in this is fitness. The word is commonly misunderstood when dealing with natural selection and evolution. Fitness isn't like I'm going out and exercising fitness. It's how well do I fit to my environment? How well am I at an advantage to surviving, reproducing, and giving my genes to the next generation? So it's probability that a particular phenotype will survive and leave offspring. So not only are you able to survive, you're able to sort of push those on to the next generation. Selectional coefficient, or little s, is the difference in fitnesses between genotypes, between, say, one genotype and the other. What's the difference in which one's has a better advantage or disadvantage comparatively? They could be equal. Hardy-Weinberg assumes they are. Can we use a calculate the change in population based upon knowing this difference? So it shows a quicker result in recessive traits because typically they are at a smaller number. Just because you can have two different ways in a traditional system to show a dominant trait and recessive traits are hidden, they tend to not show up as much. So if you have one that gives it an advantage, all of a sudden it jumps up in number very rapidly. So the numbers are going to go between 0 and 1 on the selectional coefficient, as a value of our coefficient. Can't be bigger than 1, can't be smaller than 0. So 0 gives you no selectional selection against. It means there's basically nothing happening, it's basically just neutral. Whereas 1 has complete selection against. That means if you have a value of 1 for your trait, more than likely your trait is going to go out because it probably has some sort of disadvantage causing it to die off, not produce offspring, things like that. So the fitness calculation works like this. Fitness is calculated as big W, so it's 1 minus the selectional coefficient. So if I have a disadvantage of 0.7, that means my fitness is only 0.3. That's a pretty low number. So examples would be something like this. If big A has a selectional advantage of 0.1, its fitness value would then be 0.9 because it's just 1 minus 0.1. Genotype a has a selectional advantage of 0. Well, its fitness value then is just 1 because there is nothing against it. It will work perfectly normal like it's supposed to.